Hello everyone, this is a video explaining the design process of Clemson University's ECE 496 Senior Design Reaction Wheel or RW1's project. The project was inspired by the Cubely project. The overall concept of the Cubely design was to build a cube that uses 3 flywheels to balance itself onto an edge or a corner. Our design focuses on balancing a cube only on an edge and features a single flywheel instead of 3. With this in mind, the team created these primary design objectives. Design a cube that can balance and jump using a flywheel to produce the necessary torque. Balance is defined as resting on one edge corresponding to the 4 corners of the square cross-section. Jumping is the action of moving from one resting position on a side to balancing on any of the 4 edges. We also need to interface the system with the TIVA C-Series and the Quandra Q4 board. We want to allow for easy assembly and reassembly of components, as well as have a final product cost around $300.
The cube was designed around a software control system that took as input data from different sensors on the cube. An angle describing the cube's position, the speed of the reaction wheel, and the amount of current being sent to the motor were all used to calculate how the flywheel should accelerate to balance the cube.
In order to meet our design objectives, a 3D model of all of the cube's components was made. The components include the cube frame, motor mount, flywheel, and the front and rear faceplates. The frame was made of aluminum angle iron and welded together to reduce weight while providing a relatively high torsional stiffness. Due to limited space, stainless steel was selected for the flywheel, as its higher density allows for a thinner flywheel, aiding packaging.
The angle sensor used in our project was the MPU 6050 6-axis gyroscope and accelerometer. The MPU 6050 communicates to the TIVA through a clock and data line. The TIVA then transmits an analog voltage corresponding to the angle to the Quandra Q4 board. The maximum angle the cube is designed to recover from is a 7-degree tilt in either directions.
For a DC motor, the torque the motor produces is directly proportional to the current being supplied to it. This allowed torque to be controlled by managing the amount of current to the motor. In this shot, the sine wave on top represents the current our software is commanding to the motor. The bottom sine wave represents the current being measured from our current sensor. The two are equal, so our error signal on the right stays at 0. All of the cube's components worked individually, but when we tried to retrieve angle data at a high sampling rate, the motor electronics interfered with the readings. As soon as the motor was powered, the angle sensor would quit sending readings to the TIVA controller. This made balancing the cube impossible because the angle sensor would only work with the motor electronics at low sampling rates of around 5 readings per second. A speed of around 1,000 readings per second is required for balancing. We believe the interference was caused by the close proximity of all the components mounted on the cube. Moving forward, this problem could be solved by either adding shielding around individual electronics or moving electronics off the cube.